see that this puzzle game is sort of closely connected to programming languages. And so you can think of this as being the core of what programming is actually about. And so perhaps, just as a little warm-up, since we're a small group, you can just maybe briefly introduce yourself. And maybe you can also, if you have any programming experience in some programming languages, maybe you can just tell what language that is. But if you don't have programming experience, don't worry about it. You don't really need it for following today's class. You just want to go ahead.
My name's Jean. I just started Python like 2 days ago.
Ah, perfect. So then you'll see there's some really close connection to Python, actually.
Brian, I started Python about a week ago.
You want to go?
My name is Calvin, and I started Python a week ago.
Okay. That's some Python. I'll figure out it's you.
My
Okay.
name's Amir and I don't really have any programming experience.
Okay, no problem.
My name is Jason. I did Scheme in that local last semester.
Okay, Scheme. Yeah, you'll see there's and then again there's some close connection to Scheme here as well.
My name is Sean, and I learned a little Python.
Perfect.
My name's Ismail and I have no experience.
Okay, no problem. Okay, so let's jump right in. So this is what we build programs out of. So we have essentially three things. We have old alligators, so these guys here, and they can't really do much. The only thing they can do is they can die. Okay. Then we have hungry alligators. So these are these angry-looking guys, and so they can do more things. They can eat. Okay. They can die. Another thing is they can change color. And finally, we have, since we want to get new alligators, we also have eggs, and eggs can hatch, and they can also change color. Okay. So now, how do programs look like? Well, programs are essentially families of alligators, right? So essentially, we can take, say, a hungry alligator and stack it on top of an egg, and this will give us a program. Okay. We'll see what that program is going to do, but that's a program. That's an alligator egg. So here's another one that looks more complicated. So essentially, we can stack these guys on top of each other. We can also put these constructs next to each other. Right? So for example, we have two eggs. So we have a red alligator that guards the blue alligator that guards these two eggs. Okay. And here is some huge family. Right? So essentially, you have the yellow alligator that guards everything below, and then the red alligator that guards everything below, and so forth. And here's also an old alligator. So. Okay. It's kind of part of the street. So next thing what we can do is we can put these families side by side. Right? So here we have this family that we saw before, and it's next to this yellow family here. And so when these guys are next to each other, there's something interesting. Okay, let me just quickly apologize for that. have these two families next to each other, right? And well, they are called hungry alligators for a reason. So essentially, whenever we have these guys sitting next to each other, then the right guy is going to eat the left guy. The left guy is going to eat the right guy. So you saw that this guy now ate the other family, right? And well, they're not the smartest animals, so usually when they eat too much, and then essentially they die, okay? So now the red one died, and so we are left with this, whatever is below the red guy, okay? Now, so remember the red guy ate the yellow family, okay? So now whenever something is eaten, then if we have some eggs below that are of the same color, we're essentially going to hatch into whatever was eaten. Okay, so in this case, now the red egg is going to hatch into this yellow family that we've seen before. Okay. Now essentially we have like a similar situation, right? We have a hungry alligator next to something that is edible, like an egg. So now this guy is going to eat the blue egg. And so again, this was added too much, so the guy is going to die. We're left with the yellow egg, and the yellow egg is going to hatch into the blue egg. Because the blue egg was what was. Okay, now at this point, essentially we are left to do nothing, right? Because we have only one hungry alligator, and there's nothing to the right of that hungry alligator. So at this point we stop. Okay, so this was essentially what you've seen now was a computation in an alligator egg program. So let's go through the actual rules for how computations work, right? So when we have such an alligator and egg program, how do we do the actual computation steps? And so the most important rule we have already seen is the eating rule. Okay? So the eating rule says that if we have such a large program here with many families next to each other, then the eating rule tells us that we pick the left topmost alligator. So that's this purple guy here. And so if this guy has another family next to it, okay, which is this family here, then it's going to eat that family. So note that we're only eating this family here, we're not eating the yellow family that's one further, right? Only the one that's directly next to the leftmost guy. It's also not like the green guy is actually eating something here, but it's always the topmost, leftmost guy that's eating. Okay. So this guy eats, and then you've already seen essentially what happens is that any egg that's of the same color as the guy that was eating is going to hatch into what was eaten, right? And the guy that was eating is going to die. So here we're essentially left with this new family. So we still have the green guy and the green egg, and these two purple eggs, they are hatching into this family that was eaten. So so essentially then, when we apply this eating rule to the thing that you've seen before, we're left with this. Can anyone see another possible application of eating rule? So, yeah.
The red alligator eating the green egg.
So you mean this guy?
Yes.
This egg? It's not exactly right, because remember, we always take the leftmost and the topmost. Right? So in this case, this one has something to the left, so that's why this guy can't actually eat. Right? Before this one can eat, essentially everything here would have to disappear. So this one can't eat. But you're on the right track, so maybe there's some other thing that could be in here. Any ideas? Yeah? Yeah, exactly. So the green is the topmost to the leftmost, right? And it has this other family next to it. So this guy is going to eat this guy. So then, remember what happens is that essentially this guy is going to die and this green egg is going to hatch into the yellow stuff. So essentially we're going to be left with this new program. So now, what could happen now? Yeah.
The red alligator eat the red alligator.
So this guy eats this family, right? That's exactly what's happened, except that there's another rule now that we are going to introduce. And so essentially what's bad here at this point is that, so this family here, it's the red alligator, and it will eat something that also contains the bit like cannibalism, right? You're eating something of the same color. So cannibalism is bad, you don't want to have that. So essentially, whenever we want to apply the eating rule, but the two families that are involved in the eating, they share some colors, we don't want to have that. And the way to avoid this is simply that we recolor those alligators into some other color. Maybe something that's nowhere used anywhere in the program. Right? So for example, here what we could do is we could recolor those guys into purple and whatever the color is, cyan or something, right? So what you can see here is that I recolored them, so that the colors that I pick don't really matter. So I can pick anything that's not used anywhere else. But what matters is that I sort of recolor consistently, right? I'm using essentially purple for everything that's red, and I'm using cyan for everything that's included here. So I cannot use for example, color these two guys purple because they have different colors here. Essentially everything that has different colors in the original program has to have different colors after we have. So I'm saying recoloring it like this. And now we are fine. So now we have these two families and they don't share any common colors. And now I can do the eating. Okay, so now essentially this guy is going to eat this family and then this red egg is going to hatch into this stuff here. So after this, what can I do next? Yeah.
The blue alligator can eat the yellow.
Exactly. So right, this guy is going to eat this family, and then the blue is going to hatch into the yellow stuff. So after this, next thing. Yeah.
Then the purple alligator eats the
Exactly. So again, we go leftmost, topmost. Right, this guy is going to eat this one, and then this guy is going to hatch into this stuff there. All right, and now. Yeah.
The yellow alligator's gonna eat the blue egg.
Exactly. So essentially, if you go to the topmost and leftmost, right, which is this guy here, so this one doesn't have anything to the right, so it can't eat anything. So essentially, then we go down, let's say, the same family, and we look for another one that's leftmost and sort of topmost in the subfamily, and see what that can eat. So this guy, the yellow guy, can eat this egg here, right? And what will happen is that this egg is going to hatch into the same thing. So essentially now we're left with this. And now there's no hungry alligator that has anything to the left, to the right. So that's where we stop. Okay, so now remember we had hungry alligators, eggs, and we also have old alligators, which we haven't looked at yet. And so here's a family that contains an old alligator. So essentially, you can use old alligators just like hungry alligators, so you can stack them on top of other families and sort of group other families below these old alligators. The only difference is that the old alligators, they're not actually hungry. Okay, so essentially if they have something to the right, they're not going to eat it. Right, so this is a lucky guy, it's not going to eat. But there's something else we could do here. Right? Can you see something else if you remember? Yeah?
All the alligators could die.
Yes, essentially, you're right that the old alligator will die eventually. But the rule is actually that an old alligator can only die if there's only one family below. Essentially, if there's still like multiple, essentially if the old alligator still has multiple offsprings, then it's still going to be happy around. And once there's only one family below, then it's going to die. So at the moment, there's still two families below, so it's not dying immediately. But there's something else we can do, right?
Yeah. Where an alligator can eat the blue alligator.
Exactly, right? So you still have, if you remember the eating rules, so now this guy can eat this family here. Then the red egg is going to hatch into the blue stuff. So then we are left with this. And now, you're right, so now the old alligator rule applies, which says that there's an old alligator, there's only one family below. So now this guy is going to die, and essentially the rest is just going to shift up. Okay. And then, so now this guy is out of luck, so, right, because we have another alligator that's left of it, so now this is going to be eaten. But luckily it's going to hatch again into itself, right, and then this is what we're left with. Okay, so maybe to summarize, essentially what we have are three programming constructs. We have hungry alligators, eggs, old alligators, which we can position next to each other and stack on top of each other. And we have computation rules that tell us how do we sort of transform these families of alligators, right? So the most important rule is the eating rule. Then we have the color rule, which tells us that well, if you want to eat something of the same color, we first have to recolor it. And then there's the old alligator rule, that essentially allows us to somehow group certain things together until they're done with their eating, and then they go to die. Okay, so that's all it is. Okay, so this is our programming language. And so now the question is, what can we actually compute with this, right? So it looks kind of ridiculous. We have these alligators and eggs, but what is it that we can actually do with them, right? And it turns out that we can do everything, right? So essentially anything you could do with your laptop computer, your mobile phone, everything that you can compute, you can actually compute with these alligator and eggs programs, okay? And so essentially what you're going to do now is see how we would go about this, right? How do we actually compute something that's a little bit more like something when you write a Python program that you actually want to compute. Okay, so to make things a little bit cleaner, so I mean these alligator families, they're pretty cute, but they're a little bit complicated to work with, right? It's a bit cumbersome. And so I'm using a slightly different notation that's a little bit closer to math. Sorry about that, but it's a little bit easier to work with. Okay. So essentially, if you look at this family here, then I'm going to represent this as using these kind of diagrams here. So you can see essentially this yellow hungry alligator is represented by this bar here with this variable x. And essentially, these variable, their names, they represent the colors. Okay, so essentially, you have different colors using different variables for them. So for example, for red, I'm using y, and for z, I'm using, for blue, I'm using z, and x is yellow. And so essentially, you could see I have these three hungry alligators, and here I'm just stacking these they kind of look like alligators. So it's essentially this guy's eating something that's going to hatch into everything that's represented by x, and so forth. You can also see that the eggs themselves, they are represented by these variables. Right? So essentially here, remember y stands for the color red, and then if I'm just using y directly in the subfamily, that represents an egg. Okay. And also, these old alligators I'm just representing by drawing these bars on top of the rules. Right? So remember here we have a yellow egg and a red egg, so that corresponds to just having x and y next to each other. And this bar represents an old alligator that guards this capacity. Okay, so this is my slightly more compact representation of these this family here. And I'm making it a little bit more compact by essentially merging all these hungry guys into a single line. So essentially now I have this x, y, and z next to each other. So remember, essentially this represents three alligators. That first eats x, then it eats y, and then it eats z. And so now if you're a little bit familiar with programming languages, then if you think about it, what essentially this program here represents is something that takes as input some values x, y, and z, but essentially eats those inputs, and then it does some computations on those inputs and spits something out. Right? So essentially that's exactly what this family here represents. It's a program that takes three values as input and then does some computation on it and then returns some result, which is just an output program. Okay, so let's do some computation. Okay, so our goal for today is that we want to write a alligator and egg program that computes the factorial function. Who of you has ever seen the factorial function? Okay, yeah. So a bunch of you. So this is how this is. So this common function that you will see in math at some point. And so we're using this this symbol here for the function. So essentially, this function takes as input a natural number, let's let's say n, and then it computes another natural number as the output. And what I wrote here is the definition of that function. So essentially, if the input value n is 0, then this factorial function returns 1. So factorial of 0 is 1. And for any other value n that's larger than 0, we use this recursive formula here to expression to compute the value. So what we take is we take n, and then we multiply it with the result of computing the factorial for n minus 1. So the way to think about this is that, well, you compute factorial of n by sort of going all the way down to factorial of 0, which is 1, and then multiplying it with factorial of 2, which is, so I guess this would be 1 times 1. Anyway, so essentially, you unfold this recursive definition, and then you get some expression that we just evaluate, and that's the result value. So essentially, you always start with n equals 0, compute the factorial, then you compute it for n equal 1 based on what you computed for 0, then you compute it for 2 based on what you computed for 1, and so forth, up to the value n you're interested in. Okay, let's practice this. So suppose, so I want to compute these values here, right? So let's start with 0. So I want to compute the factorial of 0. What's that word? Yeah. Sorry. 1. Exactly. Right. So we just look at the definition. If n is 0, then the result will be 1. Now, what about factorial of 1?
1.
Yeah. Exactly. So now we just apply the rule, right? So if n is 1, then this doesn't apply. So you have to go with this expression here. So we just compute 1 times factorial of n minus 1, and factorial of n minus 1 is 0.
Yeah, that's right.
Okay, yeah, so this is factorial of 0, right? And that's already what we have computed, which is 1. So we just compute 1 times 1. So this is again 1. So maybe you can give me the factorial of 2.
Well, I didn't understand that.
So I want to compute the value for 2, right?
I got what? Okay, so if n is equal to 2 minus 1 is 1, and then 2 times 1 is 2.
Exactly. Perfect. So this is 2. Next time, factorial of 3, what's that? 6, exactly. Next one is factorial of 4. 24, very good. And factorial of 5. 120, very good. So you know your tables, I'm very proud. Okay, so this is how we evaluate the factorial function, right? So there's really nothing particularly special about it, but that's the kind of functions that you build large programs with, right? Essentially, this is the kind of stuff that you would actually write in Python. Okay, so now I'm writing, the first thing I'm doing is I'm writing this in a little bit different form that looks a little bit more like an actual program, right? So essentially I'm replacing, so math people, they like to have these fancy definitions, and computer scientists, they like to write this in a way that looks more like programs. So if I have some kind of choice between different alternatives, then I would write this, for example, using an if then else expression, right? So this is essentially, I'm saying the factorial of n is the result of evaluating this expression here, where I'm testing whether n is 0. If that's the case, I'm returning 1, and otherwise I'm returning the result of this expression. It's just writing the same thing in a slightly different notation. And then there's another thing I'm doing. I want to get rid of this symbol here. I'm just replacing this with sort of a name, right? Essentially writing this as a function fact that takes an n and then computes this expression here. And then you can see here that when I do the else case, I'm recursively sort of calling the same function. So that's what was exactly what we're doing when we were doing this evaluation. Okay, so I haven't really done anything, but essentially what I want to do now is I want to write down a alligator and egg program that computes this function here. It takes an n and then gives me the factorial of n. Okay, so what do we need? Well, essentially we need all these different constructs that we're using in this definition here, right? So we need this if then else thing So we need some alligator and egg program that computes something like an if then else. Then we need numbers, right? So 0, 1, and so forth. And we need operations on numbers, and say multiplication, subtracting 1. And we need to be able to test whether this given number is 0 or not. Because that's what we're doing here when we evaluate the condition for the expression. So we have to somehow encode all of this into alligator and X programs. And then finally, what we also need is recursion. So we have to somehow deal with the fact that we somehow want to write a program that kind of uses itself somewhere inside of itself, which is kind of sounds weird, but we'll deal with that later. Okay. So essentially, what I want to do first is I want to have somewhat of a template of how the alligator and egg program would actually look like. And this is pretty much it. Essentially, think of this fact thing as an alligator and egg program that takes an n, eats an n, but essentially it eats the number n, and then it does some computation with that input. And so essentially what you see, this family here encodes this expression here. So essentially I'm writing this if then else as a single family that's going to eat the condition, which is this first family, then it eats the 1, which is this guy, and then it eats this expression here, which is this guy. So essentially I just have sort of transformed this into a first template for our alligator and egg family that's going to compute this function. So essentially if you think about sort of using a function, say like multiplication, which I replace by mult here. So this multiplication takes this as input, as first input, and then this pack of n minus 1 as second input. In this alligator and egg program, I do this just by writing them next to each other, right? So essentially mult is going to eat first n, and that's going to be the result of pack of n minus 1. And then so we're going to continue doing this basic computation. Okay, so now essentially what we have to still do is we have to define all of these placeholders, right? So I have to explain what is ITE actually stand for, what is 0, and so forth. We have to somehow express them as actual alligator and X programs again. Same for these numbers, 1 and 0, and so forth. And then finally, we're going to have to get rid of recursion, right? Because so we're defining an alligator and X family that somehow uses itself as a subfamily in its representation. And we can't really do that. So alligator and X programs, we cannot define it recursively, it cannot contain itself. So we have to somehow get rid of this fact here in the definition. But let's start with these placeholders here, essentially. How would we write a program that computes something like if then else? How do we compute a program that's computing at 0 and so forth? And so the important thing one important thing to realize here is that what's a bit funny is, right, we have these programs, say this 1 here stands for an alligator and egg program, right? Because the only thing we have in our alligator and egg language are programs, and programs can be other programs, right? And so essentially we're going to represent 1, for example, by a program. So if you think about when you work with Python, right, you have numbers directly in Python to work with, and you can then write programs that work on those numbers. But in computer science, there's really no principal difference between something like a number and a program. So essentially, if you think about data like numbers, they're just it's sort of arbitrary whether you consider them data or whether you consider them programs. It's all a matter of interpretation. And so in our alligator and egg language, essentially we only have programs, but we consider certain programs to stand for certain data values, for example, certain numbers. And this is essentially the trick for doing this in code. We say, okay, this program represents this number, just like I'm saying, okay, this symbol here represents the number 1. And then all the computation just is done in a way that you sort of simulate actual, say, for example, operations on numbers. Okay, so our starting point is we want to encode the if then else. Okay, and so forget about this part here for a second. But so remember that if then else was essentially a program that takes two inputs, right? It takes the result of testing some condition, for example, whether number n is 0. And the way this typically works in programs is that these conditions, they evaluate to something that's called a Boolean. So Boolean is either true or false. Essentially it tells us whether the condition we were checking was true or whether it was false. Right? So we essentially have these two values, true and false, that we somehow want to represent. And these we call Boolean values. And the if then else essentially takes such a Boolean value as input. And then it takes two other values, x and y. Right? So essentially this is the then part and this is the else part. And then if this b was true, then you go to the then part, so essentially you return x. And if it was false, you return y. And this is essentially what you want to implement in this if then else expression. So if then else should be in such a way that if b is true, it should return x, and if b is false, it should return y. And now the way to realize is that we define true and false in such a way that this if then else works in the expected way. Essentially we represent true by a program that takes an x and a y and then returns just x. So you think of this as a representation of this then part of the if then else function. And the false corresponds to a program that takes an x and a y and throws away the x and only returns the y. Now you can see that if I plug in this true guy into the if then else, right? So for example, if I have here if then else, which is taking a b and then it's taking an x and a y and it's returning bxy. And so if I apply this to, say, true, and say some, well, let's do this. Right, so this is true. This is my other family, and now, so this guy is going to, so the b is going to eat this family, right? And so this b down here is going to hatch into the true value, right? So what I'm doing is I'm replacing this guy here by true, and then this guy here is going to eat this one, and this guy is going to eat this one. And so what I'm left with is essentially x, which is going to hatch into x itself. Right, so of course I would have to do some renaming here. As an example, I could let's see. I guess I would have to rename this into say C and U. C. But I do the first eating, essentially I replace this by Z, this by U, this by Z. Then I'll get this, and then I'm eating the x, and so the z here hatches back into the x, and the y is thrown away. So what I'm left with is so this whole thing here simply reduces to just x. And so now if I have two more values here, say x, or maybe let's say the then part and the else part, right? Essentially now this guy would be going in here, and this guy would be going in here. And so essentially at the end, I'm only left with the t here. So this whole thing would just reduce to t. Right? So I had something, I started essentially with if then else, true, t, e. And after a whole lot of eating, I'm just left with t. Right, that's exactly what this encoding is here. So the trick is really that I'm replacing, I replace true by something that eats an x and a y and just throws away y. And I'm replacing false with something that eats an x and a y and throws away x. And then if I plug that into the if then else, like this, I get exactly the behavior I want. Right? So if then else of true, t and e gives me t, and if then else of false, t and e gives me e. Right? Which is exactly the if then else. Okay, so now let's do a little exercise. So computer science, if you think about how you build, say, a computer, so there's some processor inside that does all the actual computation, right? And so these processors, they actually build from something that's called a circuit. And essentially circuits are just, there are computations being done on these Boolean values, true and false. This true, you can think of it as a representation of 0, as a representation of the number 1, false is a representation of the number 0. So these are bits, it's another name for Booleans, bits. And everything is sort of done by computation on bits. And usually, essentially, your CPU is going to be computed by, it's built from something that's called gates. That's where the transistors sort of are composed in a way that you get gates. And these gates, they implement very simple functions that compute on these bits or booleans. And so essentially, the most important ones are and or not. And so essentially, let's see how we would actually implement them, and let's see what these things mean. So let me write down the definition of AND. So AND takes values A and B, which are Booleans, so they can be either true or false. So we have 4 possibilities. Either I get 2 times true, or I get, say, true and false, or I get false and true, right? Or I get 2 times false. So I'm just enumerating all the possibilities. And then the question is, what is AND of A, B? Okay. And the idea is that so AND of A, B returns true if both inputs are true, and false in all other cases. Okay, so essentially here I get true, and in all other cases I get false. So this is called the logical AND, and the reason is, well, is that you get checking whether this holds true and this holds true. That's why it's called AND. Only if both of these guys are true, I will return true, and otherwise return false. Okay, so now what I want you to help me with is write down an alligator ACK program, right? So I want to know what I have to put below the bar here, such that this program here at the end computes this AND function. Right? Essentially that if A and B are true here, then this whole thing should, after a lot of eating, return true, which is this guy. And so what we can work with is essentially the fact that these A's and B's, they are programs that do certain computations. Right? So essentially, for example, true here is a program that takes 2 values and then returns X, whereas false takes 2 values and returns Y. Right? And both A and B, they are in these forms. Right? So we can sort of use the fact that A and B are these programs and then arrange them in a way that they compute the correct result. Any ideas? Yeah. Okay, so maybe let me write this down here. So we have A and B, right? And so you're saying okay, and then you're saying that's it. Okay, let's test whether that's going to do the right thing. Right? So let's see. This guy does say we apply this to true and false. Okay, say A is true and B is false. Then So then we apply this to true and then false. So A will be replaced by true, and B will be replaced by false, and there's no occurrence of B. Essentially, no matter what we put as input, we get in the end A as the output. Right, so we're going to eat something into A, and if that something is true, then we're going to return true. And we're going to return true no matter what B was. Right, but now we have a problem because, for the case where A was true and B was false, you would have to return false, but you're returning true. So you're returning the wrong result. But you're on the way on the right track. So essentially, we somehow still have to take the P into account. Right? Somehow we have to do something with the P as well, so that we sort of have to check whether P is actually true or false to get the right value. And so what we can do with A is we can apply it to two things, right? And we can use the fact that we know that A, so if it is true, it's going to return the first thing, and if it's false, it's going to return the second thing. So here's one tip, okay? One thing that we see here is that if you just look at A, right? In the case where A is false, we always return false, right? No matter what B is. So if B is true or false, it doesn't matter if you already know that A is false, but you always return false in those two cases. So this means that if A is false, we know it's going to return the second value that we give to it. Right? So we give it something here, the question mark, as the first argument. And now, if it's false, it's going to return whatever I plug in as the second argument. Okay. And so, let me just plug in false here as the second argument. Right, so now, if A is false, it's going to eat these two guys, and it's going to return the second guy, which is false. And that's exactly the right result. Okay. So if A is false, which is either one of those two cases, and B is either true or false, we don't care. Now, this computation will always return false, right? Because A, if it's false, will return the second argument, which is false, so it always returns false.
So the only time the result is true is if A and B are both true.
Exactly. So now, can you tell me what I should put in here for the question marks? So this has to be something to do with B, right? Because if A is true, we still have to test whether B is also true. And then if B is true, we should return true, and if B is false, we should return false. So what should I put in here? And you have to use the fact that A, when it's true, just returns the first value. Yeah?
If the result is false and A is true, then it doesn't matter what B is. What's that result?
Yes, I mean essentially, think about, so we want to cover these two cases, right? Essentially where A is true. So we already know that if A is false, we compute the right result. So now we have to consider the case where A is true. And so when A is true, it's this function here, right? That throws away the second guy and just returns the first guy. So whatever I plug in here is going to be the result of the computation when A is true. Yeah. Just B, right? Exactly. So if I put in B here, so if A is true, I'm just returning B, right? And well now, so we have two cases, either B is true or B is false. So we are in this case here, right? A is true, and I'm just returning B. And well, if B is true, we want to have true, which is exactly the value of B. And the same here, right? If B is false, we want to return false, which is exactly the value of B. Right? So all that we do here is we test whether A is true, and if yes, we just return B as the result. And otherwise, it's so there's no hope for making the whole thing true, so we just return false. So this is how it ends. Yeah.
But what if A is false?
So I mean, just think about it. So if A is false, it's this program here, right? So it's going to eat X and Y, the two things that I'm plugging in, and it's throwing away the first guy and just returning the second. So it means that if A is false, it's eating those two guys, it's throwing away the B, and it's just returning the false. And that's exactly what we want. Right? So that's it. Okay, so let's do one more. Time. So there's another one that's sort of similar to and it's called OR. And the idea is that for OR we're testing whether one of them is true, either A or B, and then we're returning true, and in all other cases, well, there's only one case essentially where both of them are false, and then we're returning false. Essentially what I'm doing is I'm replacing this by true, and this remains false. And so I'm erasing this stuff. We have to do a slightly different computation, but it will be very similar to what we just wrote down for A and B. So again, we have to somehow combine A and B in the right way so that the result is the correct result according to this table here. Any suggestions? Yeah.
AB true.
Let's write this down. Let's see. So suppose A is false. Okay. Just 1 second. Let me just go quickly through it. So suppose A is false, then there's the case where we have to return false, right? Namely the case where B is also false. So when both are false, we should return false. But now if A is false down here, we're eating these two guys, we're throwing away this one, and we're returning the second. So in that case, so if A is false and B is false, we actually return true, right? And that's the wrong result. But you're on the right track. Do you have a suggestion?
No.
So but it's almost correct. So there's a little change that you have to do. Yeah, true. Exactly. And so if all we have to do is we have to flip these two guys. So now if A is true, then if you look at it, it doesn't matter what B is, we always return true. Right? So that's exactly what will happen. And if A is false, then it depends on whether B is true or false. Right? Namely, then if B is true, we return true, and if B is true, we return true, and if B is false, we return false. That's exactly what we get. So it's exactly the value of B, so we just return. Okay, so the last one is actually quite simple. All that it does is it sort of flips the values. So that if you get in true, you want to return false. And if you get in false, you want to return true. And so here is one way of doing this. So essentially what I'm saying here is I return a new Boolean, so the new Boolean value. And remember, they're always of this form that they eat two values x and y and then return either x or y. Essentially what I'm now doing is I'm just rewiring the B. Essentially I'm just saying, okay, take that B and now flip x and y. And so now if B was true, then this is going to return y. So I get x, y, and y, and that's false. And if B was false, I'm returning x. So I have x, I eat x, y, and return x, and that's true. So this is negation. So you can see essentially we can build circuits using alligator X programs. Essentially we could encode something like a processor into these alligator X programs. Okay, but let's make it a little bit more interesting. So we have these booleans, but you actually also need numbers, right? You want to have a factorial function which makes numbers and does something different. And so you also want to encode those into programs. And so here is here's the basic idea. Okay. So if you think about, so what I'm doing here is I'm saying z. It's just some name. I'm saying z is the value 0, the number 0. And then s is what I call the successor function. Essentially, it's the function that takes in the number n and just adds 1 to it. It returns the new number n plus 1. And now, of course, you can just sort of compute all value, all natural numbers, just by starting with z. So 0 is z. and then 1 is S of Z, and then 2 is S of Z, and so forth. Right? Every number can be just computed by applying S to its to the number that's once wrong. Now, this is now the key idea for representing numbers. We are representing numbers as programs that take an S and a Z as input, and then apply S n times to Z. So essentially, we represent the number n as a program that takes an S and a Z, and then applies the program S n times to Z. So essentially, we represent the number n by a program that does something n times. Okay. So here's how this goes. So the number 0 is represented by this program here. Essentially, we get an S and a Z, and we apply S 0 times to Z, so we just return 0, S and Z directly. So you can see that it's actually the same program that we used for false. Right? We take an S and a Z, we throw away S, and we just return Z. But we now say when we look at numbers, we use the same program to represent the number 0. And for the number 1, we now take an S and a Z, and we just apply S to Z. We just add S Z. And for 2, we just do this 2 times. Right? So now we have we apply S to Z once, and then regard this by an alligator, right? That alligator, whole alligator, and then we let S again eat the result of this. Right? So if you think about if Z was actually the number 0 and S was actually the number that adds 1, then this computation would give us 2. That is the value that you want to represent. So how would we do this for the value 3? So I want to have now a program that essentially, so I represent the number 3 by a program that takes an S and a Z and then applies S 3 times to Z. That's essentially what I'm doing is I apply it once, then I apply it another time to the result, so this is 2. And then I take that and apply it another time, so this is 3. So that's the program for 3. If I wanted to have 4, I would just go on like this, so I would make another application. Okay, so now let's see. We want to, yeah.
How going for the second one? The second one.
This one?
No, that one.
This one?
Yeah. Doesn't the S eat the bar?
Yeah, I mean, so remember, so it eats the whole thing, right? So whatever S is, it eats. You think of it as eating this computation here. And so remember, so suppose Z and S were actually these. So Z was actually 0, the number 0, and S was actually a program that takes a number and adds 1 to it. And essentially what we're doing here is this is a function. This S here takes whatever the result of this computation is, and then adds 1 to it. Right? So, which means that if you look at this computation here, well, it takes 0 and adds 1 to it, which is 1. So that's the result of this computation is 1. And remember, this guy adds 1 to its input, so we get 2 as the result. Yeah.
So the higher the number gets, the more.
Exactly. So yeah, we're just going to stack them more and more, deeper and deeper. Right? And we get the stack here is essentially of the. So we have the same height as the number we want to represent. Right? So we have a stack of height 3, and that's the number we want to represent. So you apply S3 times to Z. Okay, so now what you want to do is you want to encode these operations on numbers. Right? So for example, you want to be able to add 2 numbers, you want to be able to multiply 2 numbers, you want to let's say, just add 1 to a number, and say we want to have this 0 test, right? That tests whether the number is 0 or not. So essentially the 0 here takes a number and then it should return true if n is 0, and you should return false in all other cases. So this one is a little bit more tricky, but let me just write down the program and then we can convince ourselves that it's computing the correct result. So remember, n is a number, so it's a program of this form here. Like we just apply whatever it gets as first argument, n times 2 the second argument. So if this guy is the number 0, which is this program, then what will happen is that we will just throw away the first guy and we'll keep the second guy. So in that case, the whole thing evaluates to true. So that's exactly what we want, right? So if you plug in the number 0, we should return true. Now, if it's any other number, right, what will happen is that we take this guy and we apply it to 0. So if n is 1, then it's of this form. So it takes this guy here, that's going to be our S, and it takes this guy here, it's going to be our Z. And then it applies this guy to this guy. So essentially we're going to beat, so this true goes into X, and then what we're returning is just false. And then if we just do this one more time, it doesn't matter, we still compute false. So any other larger number will also return false. So no matter what n is, if it's non-zero, it's going to return false. And that's exactly how 0 does. Okay, so here's how we would do +1. So essentially we return a number, which is something that takes an S and a Z, and then it should apply as n plus 1 times to Z. Okay. And we're just using the fact that, well, if n is a program that takes an S and a Z and then applies as n times to Z. So we just get that by calling n with S and Z. So this essentially gives us the number n, and then we just apply s one more time on top of it. So essentially this is how, you can see that essentially this goes from this guy to this guy. Right? That's what the +1 does. Essentially if the +1 takes this as input, it's going to return this as output. Takes in 2, it's going to return 3. And it's going to take 3 as input, it's going to return 4. So that's +1. Any ideas how plus would be? Say essentially I want to be able to return the result of adding the numbers n and m. So essentially I want to get a function that takes an s and a z, and then does some applies as n plus m times to z. And I can use the fact that n and m sort of do the work for me. I just have to combine them again the right way. And in particular, I can also use, for example, the plus 1 function. Right, so this would be one way of doing the computation here. So let me just show you two versions here. So for example, I can take, so this is kind of the basic way of doing it, right? I just take, I want to return a new function and a new number, and the numbers are always something that takes an s and a z. And then what I do is I first compute, I apply as m times to z, so that essentially gives me the number m. And then I apply as, again, n times to the result of that. So essentially what I'm doing is I'm computing first the number m, and then I'm adding n on top of it. Right? By essentially applying as another n times. So first apply as m times, and then I take the result and apply as another n times. So you get a function that applies the s to z m plus n times, which is exactly the value here, which sort of computes the value of plus n. And so here's another way of doing it, so by reusing the +1 function. So what I'm saying here is I'm adding one n times to n, which is another way of computing n plus n. And so multiplication is kind of similar, so we kind of now say, so the function, instead of applying s here, I'm applying a function that adds as m times. So essentially this is the function plus m, takes an input and then adds n to it. And then I do this n times 0, so essentially I'm computing n times, so I take 0, I apply plus m one time, apply plus m another time, plus m another time, plus m another time. I do this n times, so I get n times plus m, which is n times m. So that's multiplication. I mean, it's sort of a little bit daunting, but you know, you can really just take these guys and just plug in, say, some values. So you take this guy, you plug in 1 and 2, and you just apply the eating rules and all the rules, right? And what you would end up with, in this case, is essentially the number 4. Sorry, the number 2. If you take these two guys and you plug them into mul, you end up with the number 6, with this kind of stack program that represents the number 6. Okay, so I'm skipping over subtraction. Subtraction is a bit more tricky, but you can do it. And I think we're running out of time, but so let me just quickly wrap up the main part of this. So essentially, remember what you wanted to do is you wanted to have this kind of program, right? This alligator X program that represents the factorial function. What we have done so far is we gave programs for representing all these things here, right? Like if then else, is 0, multiplication, minus, and so forth. And we had the representation for the number 1. So really the only thing that we're left with is this problem that we somehow do this recursive call to the program itself. Right? We have to get rid of that as well. And so the trick for this is that we rewrite our program in a little bit. It's essentially, so suppose, say you want to compute the factorial function, and you don't really know how to compute it for, so you know that if someone told you how to compute the factorial of n minus 1, then you know how to compute the factorial of n, right? Because you just apply the rule. So if someone told you how to compute factorial of n minus 1, then, well, you get factorial of n just by applying n to it. And so that's the trick that we're doing here. We find a new function that essentially asks as input a function that computes the factorial function for any value smaller than n. And then we can just do this computation.
So you're putting a function in the function?
Yeah, so that's another nice trick in programming languages, specifically if you're doing Python and other, or Scheme and these types of languages. So remember, program data, no difference. So we can have functions and take other functions as input. That's perfectly fine. That's exactly what we're doing. So you find a new function, it takes the function as input, and this function here tells us how to computes the correct value for n, correct factorial function for all values n, all values smaller than n. So this is one way to think about this. So we can write, say, fact0, we define this function that always returns 0 no matter what n is. So think of this as a function that always returns the wrong result no matter what n is. Right? Because factorial function always returns something that's larger than 0. It doesn't never return 0, so this is always going to get the wrong result. But now, see what happens if I define this fact1, where I just take this fact function here, and I plug in this function and n, right? Now, this is just going to evaluate this expression here. So now if you take this guy and you plug in 0 for n, it's returning 1, which is the correct value. It's just that in all other cases, it's going to return the wrong value. It's going to return 0 again. So this is going to compute the right value for n equals 0. Now we do this one more time. So I plug in fact1 instead of fact0. Then I'm going to compute the values, the correct value also for n equals 1. And so if I keep doing this, then I compute the value essentially for any value n. I just do this n times, and then if I apply this to n, I get the right result. And so, just for wrapping up, so essentially the way to deal with this is that we write a program that we call this fix. Okay? And this fix program takes this fact as input, and it's going to do some eating, and what it's returning is fact applied to what we started with. Essentially, this is going to be some kind of replicator. So it takes something as input, and then it takes that input and applies it to whatever we started with. And so if we do this one more time, essentially we do the same thing here, inside here, we end up with this guy. So we apply fact one time, you apply it another time to whatever we have here, and so forth. So if you could write a program that fix that has this property, then essentially what we can do is we can plug, essentially this is going to compute the factorial function. So essentially you can take this and you plug in n, and at the end it's going to compute factorial of n. So all this is doing for us, it's sort of applying fact n times to itself, so that at the end when we plug in the value n, it's going to compute the factorial of n. And so I don't really have time to go through this, but essentially there is an expression that you can write that does exactly that. So if you write down this fancy program here, so that's an alligator lag program that takes a g, say like fact, and then does this computation here. So you can see there's some fancy replication going on here. If you plug in, say, fact into this expression here, and you do the eating rule, you'll see that exactly it's going to compute this value. And then you can just go on forever replicating this fact function, applying it to itself. Okay, so then at the very end, essentially what we can do is we can define this fact program as this expression here. Essentially, we take now this function fact as input and the n, and then we just do the computation. So we broke the recursion here, right? So this guy is just another input. And then we compute the factorial function by applying fix to fact and n. And this is going to compute the right result. And so I'm out of time, but so if you want to see this in action, essentially what you're seeing here, this alligator and egg language, is what you call in computer science the untyped lambda calculus. Okay, that's a fancy word, but it's essentially the foundation of many, many programming languages. So in particular, Python is one, so you mentioned schemes. Scheme is one language that you build on top of these ideas. And there's a whole bunch of other languages. And one is, for example, JavaScript. You may have heard about this. Essentially, that's what's running all your browser applications, more or less. It's based on these very simple ideas. And you can actually take all that we have written down here, you can directly transform it, say, in a JavaScript program, and then run it in our web browser. And it's actually going to compute really the factorial function. So I wanted to have a little demo, but it's going to take too much time now. But if you want to see this, just send me an email, and I'll be happy to send you this JavaScript program that you can run and see that it actually computes the right result. Okay, so let me just write down my email address in case you want to see this. I can also give you the slides.